In this video, I'm going to demonstrate the solution to a constant acceleration problem using a velocity versus time graph. Here I have two buggies. Buggy number 1 is accelerating, and the information is given in that table. Buggy number 2 is with constant motion, or with non-accelerating motion. Alright, so let's get to it. When dealing with graphs, you pretty much start the same way all the time always. You just start labeling the different parts on the graph. And so we've got the initial and final velocities, an arbitrary time. That's a time interval. The displacement is the area under the curve. And the slope, by definition, is the acceleration. Alright, and for the second buggy, it's not nearly as interesting because the slope is equal to 0, but that's not really its own fault. Displacement is still the area under the curve, and that is our time interval. Okay, once we have everything labeled, we're ready to begin. To solve this problem, I'm going to represent the displacement in the form of the trapezoid equation. Delta x equals the average of the two bases times the height. And I run into this problem right here. I do not know the final velocity. And so to get around that, I'm going to go back to my definitions and make a substitution. By definition, the acceleration is the change in velocity over time, and I can expand that like this. When I solve for VF, I can substitute here, and I can substitute here. That's how it works. So when I make that substitution, it gets a little bit messy here, but hopefully you are keeping track of your symbols and drawing neatly, because neatness really helps a lot when there's so many different terms. What I'm going to do is just start breaking this down algebraically and simplifying the expression. I've got VI plus VI there, so that's going to be equal to 2 times VI. And then I've got A times delta T. And I still haven't lost that 2 yet. What I'm going to do is I'm going to distribute the delta T's. So 2 times VI times delta T plus my acceleration times delta T, which I'll write that way, all over 2. Last step, which is the easiest step, I guess, is just to simplify and reduce the fraction. 2 divided by 2 equals 1. And nothing to reduce here, so the reason why I did this last step is because this is a very common form of the equations, and we just like it this way. A lot less work for the second buggy with constant motion. The displacement is in the shape of a rectangle, so that's just base times height. Alright, so that is all I really need to do for the constant motion part. So here is where we actually need to start being thoughtful, and this is where most people get stuck. The common mistake on these problems is people setting the displacements of both buggies equal to each other and trying to solve, but that is not correct. That would be a hell of a coincidence for both of them to have had the same change in position. Seems really random. So what I need to do is I need to come up with something better. And so what I'm going to do is go back to my definitions. The displacement is equal to your final minus your initial position. And why I'm doing this is that when they collide, xf is the same, and that's kind of the whole point of the question. So what I'm going to do is I'm going to substitute what delta x equals into my trapezoid formula. So here we go. and just solving for xf, just adding xi to both sides basically. I have a form that has the motion of the blue buggy, solving for xf, doing the same thing for the green buggy. It's pretty simple. I have the luxury of using color coding to keep track of my starting velocities and positions, but you may need to consider using subscripts if you're just using a pencil, because there's a lot of symbols here and some of them are shared. For example, the initial velocity of that buggy is not the same as the initial velocity of that buggy, and so oftentimes you would use subscripts, but I'll let you decide that one. Alright, what I'm going to do right now is I'm going to substitute the green xf into the blue xf, and I've got vi times delta t plus xi, and that is going to equal 1/2 a delta t squared plus vi delta t plus my starting position for the blue car. Alright, at this point I'm going to start substituting what I know. For example, the initial velocity is 5 meters per second times delta t plus 0 meters equals 1/2 times 2 meters per second for every second times delta t squared plus 1 meter per second times delta t plus 1 meter. Now this looks like a hot mess, but notice that we have like terms that we can group. This bit right here will group nicely with this part right here. And you can say the same about this, but this isn't really a very exciting part because it equals 0. But if it didn't equal 0, then you would group that one too. Alright, so what I'm going to do to solve this problem and set up a quadratic formula is just make one side equal to 0. So I'm going to subtract 5 meters per second times delta t from the left side as well as the plus 0 meters. So 0 equals 1/2 times 2 meters per second. Most of you guys will probably reduce that. 1 minus 5 equals -4. And let's just do that reduction right now. Delta t squared minus 4 meters per second times delta t plus 1 meter. There are many ways to solve for t here. You can use a solver on your calculator, you can graph and find zeros. If you go back to the blue and the greens, you can find where they intersect, or you could do the quadratic formula, or you could use other various versions of that, but the easiest way, or the most straightforward way, I would guess, is a quadratic formula. It works all the time without the need of a calculator. And if you've forgotten that, in this case, t equals -b plus or minus the square root of b squared minus 4ac all over 2a, and a, b, and c are just the coefficients in front of the squared, the t, and the non-coefficient. Anyways, back to this. When I run this through my calculator, I realize that there's two solutions for time. Sometimes there's 2, sometimes there's 1, sometimes there's none. And that's okay. You just have to be smart about interpreting the data. If you have a negative time as one of your solutions, it's probably not correct. It's outside of our domain. If you notice, our velocity versus time graph starts at time equals 0. Alright, once you get your times, you're halfway done, but mostly done at the same time. I also wanted to know where the buggies are located when you collide. What you need to do to finish this problem is just substitute these time values into one of these two equations. Doesn't matter which one you do because it will be the same answer. And so I'm just going to take out my calculator and just let me just finish the problem here. Alright, so the first collision happens at a position of 1.3 meters from the origin, and the second one happens from 18.65 meters from the origin. And this is how you do it. I hope this has been helpful. Thank you guys very much.